All right, we're starting here with looking at the zeros of polynomials. Last time we had just looked at what in general polynomials were, and we learned and looked at our leading coefficient to figure out what the behaviors were at the ends. And now what we're going to do is look at the zeros of the polynomial functions, and then we're going to go and put all of this together to basically figure out the general shape and graph out what these polynomials look like. It's not, of course, going to be a perfect graph, but we'll get pretty close. So if we look at this, it says, what are the zeros of a function? These are essentially the x-intercepts of your graph. Okay, so you graph it, and the x-intercepts are where that's going to happen. You find this by setting f of x equal to 0. So you're finding this, that's it, and that'll get it for you. Second, some of these zeros will repeat themselves. They'll be in there more than once. And so when that occurs, we actually say they're occurring multiple times. So we say they have a multiplicity. And so the multiplicity of a zero is going to just tell us how many times that specific associated factor occurs in it. So if you have something like, like an x minus 3 squared, then you actually get that x minus 3 twice. It occurs twice. And so you would say it has a multiplicity of 2 because it's counting there as 2 of the factors for it, or 2 of the zeros. And so when that occurs, if we have an odd number for the multiplicity, so if it's odd, like 1, 3, 5, 7, 9, if that's the multiplicity, then the graph is going to cross the x-axis. If you want an example of this, you can just think of f of x equals x cubed. If we look at x cubed, right, it looks something like this, and it crosses the x-axis like that. So cubed is an example of an odd multiplicity. That x cubed would have a multiplicity of 3. And then if it has an even multiplicity, then the graph just touches and turns. An example of this would be x squared. So x squared graph is that parabola, and it's going to come down and touch and then go back that way. So x squared would look something like that. That is a touches it and turns, and this is a crosses. All right, so even multiplicity, so it's to an even power, then it touches and turns. Odd multiplicity, it's going to cross it. All right, so let's do a couple of examples here. They tell us to find the zeros for each polynomial and give the multiplicity for each zero, and then state whether the graph crosses the x-axis or touches the x-axis and turns around. All right, so we look at this one. The first thing we want to do is we want to set this equal to 0. That's what we're going to do. So essentially, we're going to set equal to 0, then solve. That's how we're going to find our zeros. And so I'm going to set that equal to 0, and then I'm going to look at this and I'm going to say, all right, this can be factored. And I can factor it to x, x plus 5 times x minus 1. Because -1 times 5 is -5, and -1 plus 5 is 4. So that's my factor. It factors nicely right there. So then this one over here tells me that x plus 5 has to equal 0, or x minus 1 has to equal 0. So if either one of those two things is true, then we will get a 0. So over here, this would be x equals -5, and over here it'd be x equals 1. So these right here are our zeros. Remember, the zeros are opposite in sign to the factors. These are the factors up here. The 5 and the -1 are the factors, and then the -5 and 1 are the zeros then. So those are our zeros. And now we just need to look at the multiplicity of it. And so to do that, we're basically going to look at what power is up here, right? Right up there. And if we look, the power that would be right there, we don't really write it, is the first power. And so that tells us that this x equals 5 has a multiplicity of 1. All right. And since it has a multiplicity of 1, it's going to cross. It crosses the x-axis there. It's not going to just touch it and turn. If we look at the x minus 1, that also has an exponent up there of 1. And so this would have a multiplicity of 1 as well, and it will also therefore crosses the x-axis. All right, so let me do one here real quick where we see a multiplicity not equal to 1. So I'm going to skip 16, and I'll go down here and look at 17. So if we look at 17, it's already factored for us. So this one will tell us x equals 5 is a 0, because x minus 5 has to equal 0. So x equals 5 is 0. This one over here tells us that x equals -6 is a 0. So these are our two zeros. All right, I skipped the, x plus 6 equals 0. For this one, I have a multiplicity of 1 again, because that would be a 1 in that exponent. And therefore, this crosses. But here on this one, I have a 2 right there. That means that this has a multiplicity of 2, and therefore it will touch and turn, which I'm going to write as just TNT, touch and turn. It's going to touch the axis and turn back around the way it came from. Okay, so there's a couple examples for you. So what I want you to do is go ahead and take a moment and try 16 and 18 and see if you can write all that out for those while I pause this. All right, so taking a look at these three, we look at this first one here. So the first thing we do is set it equal to 0. And then what we want to do is look for anything we can factor out. I can factor out a -3 from both terms, and I can also factor out an x to the 4th from both of those terms. And what that'll leave me with is x minus 1 then, right there. Or not -1, I'm sorry, x minus 4. All right, so if I were to multiply that -3x to the 4th back in, I'd get -3x to the 5th, and then plus 12x to the 4th. So that's a good factoring. I can divide both sides by that -3, so I don't have to worry about that -3. And so what I have here is I have an x to the 4th, which tells me x equals 0 is a solution. And then I have this x minus 4, and that tells me that x equals 4 is a solution. So I have those two. So here are my zeros, right? For this x equals 0, it has a multiplicity of 4 because we have that 4 right there. All right, because it's to that 4th power. You could also write x to the 4th as x plus 0 to the 4th to kind of show you it if you want it always in that term where it's that power outside of the parentheses like that. That's what that essentially is. And so this tells us this has a multiplicity of 4. 4 is an even number, so this will touch and turn. Okay, that's what that one's going to do there. For the x equals 4, that has a multiplicity of 1, right? It has a multiplicity of 1 because this exponent up here is a 1. And so then that tells me that's odd, and therefore it crosses the x-axis at that point, at x equals 4. All right, so there's that one. Now this next one can be a little tricky too, kind of a, whoa, where do we go about factoring that thing? And the trick is to look at the first two terms here, and I see that I can actually factor out an x squared out of the first two terms, and then these second two terms, I can factor out a -4. And if I do that, what I get is an x squared times x plus 3 right there. And then I get a -4 times x plus 3, right? Oh, I forgot to do the equals 0. Okay. And by doing that, you see that I have this x plus 3 and x plus 3. And so it's common in both of the terms I have there. I have an x squared times it and a -4 times it. So what I can actually do is factor that x plus 3 out in front and leave myself the x squared minus 4, just like that. And then that will equal 0. But we're not quite done, because this right here is actually the difference of two squares, which, if you remember, a squared minus b squared, this actually factors to a plus b times a minus b. And so this would become, we'd keep our x plus 3. The x squared minus 4 would become x plus 2, not 4, sorry. X plus 2, x minus 2. And now we have this fully factored. All of our x's are to the first power, and then we just have to look at the exponents up here to figure out each one's multiplicity. And so we get x equals -3 as a 0. We get x equals -2 as a 0, and we get x equals 2. So these, and that's where they came from. Just like that. These are our zeros, and it's just a matter of looking. They each have a multiplicity of 1. So multiplicity of 1, multiplicity of 1, multiplicity of 1. All of them do, because they all have that same exponent to the first power up there. And then that means they each cross. So it crosses, 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 just like that. Okay. And so then we're going to go ahead and do this next one, and then I'll look at questions. So if we look at this one, that one might be a little tricky to look at first too, but we can actually factor this one. This, again, you set it equal to 0, just like that. And so what I'm going to do is I'm going to rewrite it this way. This is x squared squared minus 2x squared plus 1. So if you look at it this way, we have a something, we have an x squared squared, so that's something squared minus that same something. I could almost say something like, if I had a equals x squared, I could write this as a squared minus 2a plus 1. And that right there is something we can factor. So I'm going to treat the x squared as though it's one thing and actually do the factoring according to it. And when I do that, I just have to ask myself, what multiplies together to give me 1, but adds up to give me -2? And so that's going to be x squared minus 1 and x squared minus 1, just like that. Of course, equals 0. And then when I look at this, it's still not fully factored. But again, what do I have? I have the difference of 2 squares. So that means that this one right here is going to give me x plus 1 times x minus 1. And then this one over here is going to give me an x plus 1 and an x minus 1 as well. So they each gave me an x plus 1 and an x minus 1. And so I have an x plus 1 and an x plus 1. That's an x plus 1 squared. And I have an x minus 1 and an x minus 1. That's an x minus 1 squared equals 0. Therefore, from this one, I get x equals -1 as a 0. And from this one, I get x equals 1 as a 0. So these are my two zeros. They both have a multiplicity of 2, because that exponent up there is a 2. For both of them, multiplicity 2, and therefore they both touch and turn right there on the graph. All right, so that's how you do those three. I'm going to go ahead and see if there are any questions, and so I'm going to pause for just a moment. All right, so let's bring everything that we've done so far together and see if we can figure out what this graph looks like just based on what we've done so far with not just today, but in past classes as well. So first, we're going to look at the leading coefficient test and determine the end behaviors of the graph. So if I look at this, I see that this has a degree of 3. So the degree is 3. That's odd. And therefore, I want to think x cubed. That wasn't a very good cube. Think about the x cubed graph. But I also look out front and I see that I have a negative there. And there's no other negatives on any of my x's or anything like that. So that means if I were to multiply this all out and expand it, I'd have a negative in front of my x to the third power. So I have an odd x to the third, and I have the negative. So what that does, so it's odd, and then it's negative, right? And so negative says then think negative x cubed, right? Because x cubed looks like this. That's x cubed, right? But we need to flip it over and think that one. negative x cubed looks like that. So that's the example we want to look at, is negative x cubed, right? Oh, this was a negative coefficient, is what I meant there. And so that means it's going to rise to the left and fall to the right. Or as x goes to negative infinity, y will go to positive infinity, and as x goes to positive infinity, y will go to negative infinity. But either way, as you think there, rises left, falls to the right. Next thing, it says find the x-intercepts. This is going to be where we find the zeros, right? And figure out their multiplicities to determine whether or not they cross or touch and turn at those locations. All right. And then that's what we're going to do. So we take our function up here and we set it equal to 0. Thankfully, it's already factored for us. So we get an x equals 5 as a 0 and an x equals negative 6 as a 0. This gives us the x equals 5. This gives us the x equals negative 6. For x equals 5, we have a multiplicity of 1 because its exponent up there is a 1. Therefore, we have an odd. Therefore, it's odd. And therefore, it crosses. It crosses the x-axis there. And then what we have is a multiplicity for x equals negative 6. That's a multiplicity of 2 because that exponent is a 2. That's even, and therefore this will touch and turn at that location. All right, so we have our x-intercepts right there. Next, we need to find the y-intercept. We do that by plugging in x equals 0. So we take this here and we have y equals negative 3, and then I replace x with a 0, and then I replace x, oops, I wrote x, I replace x with another 0, just like that, plus 6 squared. So this is negative 3 times negative 5 times 36, just like that. This 15, so I have a 15 times a 36. So that's like 15, 3.5. That should be 540, pretty sure. Double check me on that. And then determine whether the graph has y-axis symmetry, origin symmetry, or neither. So in other words, determine if it's even or odd. Remember, even functions, right? Even functions is when you substitute every x with a negative x, and then it turns out to just give you the exact same equation back. Odd, that's even. If that's true, odd functions is if you replace every x with a negative x and you get the negative of your original function. So the even function gives you symmetry around the y-axis. The odd function gives you origin symmetry. But if you look at this one and you try plugging in, swapping x for negative x, you'll find you get neither. It doesn't end up equaling its original self or equaling the negative of its original self. So it's neither, has neither one of those symmetries to take advantage of. And then the last thing is, let's graph this polynomial. So let's take a look at what we have. So what I have here, and I'll do this, maybe this part in, I guess I'll try and color code it for you here. But what I have is, I've got this, rises left, falls right. So I know I'm going to be doing something like that over here and something like that over here. That's as I go to the left and as I go to the right, it's going to do something like that. The next thing I have is that I've got these zeros right here. So at x equals 5, that's a 0. And at x equals negative 6, that's a 0. So those are x-intercepts. If I look at the x equals 5, I see that it crosses, right? So if I look there, it crosses. So I know it's going to cross like this because out here it's going down. So it has to cross in that direction in order to do that. And then over here at the other one, it's a touch and turn. So it's going to do something like that. And it has to be a touch and turn that way, not a touch and turn this way, because the graph up here is above. And we have no other x-intercept, so there's no way for it to get back up there and do that without crossing the x-axis again, and it never does cross the x-axis again. So it has to be facing upward. All right, so I know that those two have to be like that. Then the last thing I can do is take a look at the y-intercept. That was right here. That was at 540. So we'll just pretend I'm way up here at 540. I know our axis doesn't quite go there, but something like that, way up at 540. And then the last thing is just to sketch this graph in. So I know that I'm going up this way there, and it's kind of like a connecting the dots. Let me do that again. Got real bad. It's kind of like a connecting the dots. I'm going to combine those two together. I know up here I have to go up and cross there, and then I have to turn around and come back down. So I have to come back down like that, then I have to cross that axis, and then I have to go down that way. And so if I do that, I have a basic shape of the graph. Again, like I said, it's not a perfect graph, but it is the basic shape of that graph. That's what it's going to do. Of course, this would be like way up higher, way off the page at 540 if this scale was actually a 5. But I don't have room for it, so we'll pretend that that's 540. Okay, so that's basically the shape of that graph just from the stuff that we have done so far. All right, so I'm going to pause and check for any questions.